All right, so now we're going to talk about evaluating radicals, okay? So evaluating radicals, first you understand the fact that we're dealing with basically simplifying and breaking down current radicals with different root values. So we are no longer in the realm of just looking at the square. That is gone. We are now going to see things like cube roots, fourth roots, fifth roots, sixth roots, roots with exponents inside of the root. So fifth root of x to the fourth. You're going to see some crazy combinations. The idea is it's this simplification. Where I see a lot of people make their mistakes is they'll basically mix up 4 and 5, the roots with the index, and the exponents with the index, and they'll get them backwards and they'll put them upside down. Okay? So how do roots work? Roots undo exponents that are equal to the index. All right? So basically, with these, you're just looking for cancelization. So, for example, in the first one, you'll notice that the cube root of x to the third, 3 is just going to cancel, and you're left with x. That's it. Now, the reason that happens, I'll show you on the next one. Next one implied 2 in the front, so it's square root of x squared. The reason why is if we were to convert this back to its fraction form, it would be x 2 over 2. Any number divided by itself is 1. And that's why it cancels. I think, remember, I showed you that once before in the previous sections. So when you see a exponential value that is also matching the index, you should be smiling. Great, cancel it, get it out of there, done. Okay? And that can happen, for example, you can have the square root of AB squared C cubed. The B will come out completely fine. Just pull them out of there, leave the other stuff in there, and then evaluate it. Okay? Makes life a heck of a lot easier. Okay? Same thing for the next one. Fourth root of 4. The 4's cancel. You're left with just x. X, 4 over 4 becomes x. However, if you have a number, on the other hand, this is a little bit of a different story. Okay? I'm just checking something. Okay, good. For some reason, I thought the mic was off. We're good. Okay. So, for square root of 25, okay? Now, there are 2 ways to do this. One, you can know it's a perfect square. Say it's 5 and 5. Done. However, mathematically, what's going on behind the scenes is really this. Okay? There's an implied 2 here. Yes. And what we have is we actually have 5 squared. There are 2 5s in there. So when you guys are breaking down your numbers, right, into squares. So let's say you had the square root of 150 and you broke that down to 10, 15, 2 and 5, 3 and 5, 5 get out, 2 and 6 left over. What you're actually doing is you're basically listing out all the prime factorizations for that number and then counting out the numbers you could take out of it. I think we did this once with y, I want to say, in unit 4.1.2, where I showed it to you briefly again. I've been kind of sprinkling it out in the first 2 sections because I didn't want to overwhelm you with it up front because, honestly, it's kind of a pain in the butt. So now that we're here, we can start now manipulating these radical expressions to better suit our situations. And I promise you, it is a lot easier to FOIL a number that has a fraction than it is to FOIL the radical. You can kind of see where this is going. Think back to the problems we did in the previous section, and you're thinking probably yourself, wait, if I could turn them into, a fraction, so I would have had 4 to the 1/2 times distributing to that 2 things. Yeah, that's a heck of a lot easier. It is. And I can show you guys some more tricks there, how you can actually add exponents together, because if you have 1/4 plus 1, just convert it to 4 over 4, 4/5. Ironically, you get back to that point. But you basically manipulate these problems in a way to better suit you if you want to deal with radicals or exponents. Either way is fine as long as you get the answer. Well, relatively accurate, I should say. Now, with all that said, the 2's would just cancel, and you're left with 5. So the general rule of thumb is this. Okay, n, x to the n, okay? The n will cancel out so long as the n is the same, and you're left with x. So what I would do on that one is I would write this little asterisk and write this. N must be equal to root. All right? And that's pretty much it there. So now with all that said and done, with all that complete, all right, I'm just going to move it up to this far so we can read some of the instructions. Let's talk about the steps. So this is the evaluate expression steps that you need to follow when you go through and solve for one of these guys in here, okay? First step is convert into radical form if necessary using the equation we looked at the front, see front page. Find the prime factorization of the radicand, the inside root, first prime numbers, okay? So basically these sets of numbers combined will equal that term, as I've stated before. 2s, 3s, 5s, 7s, etc. Okay? Rewrite the radicand in a power equal to the index. Okay? Which we basically did up here with 5. Okay? Use the property x nth root of x to the nth equals x to simplify the root. Cancel out, make sure they're the same. Finally, evaluate further if needed. Basic simplification. Okay? So let's go ahead and do the first one. I'll go relatively easy here, and you'll see what you're going to be doing. This is basically nothing new, though. We've been doing this with other numbers, just as perfect square, just as square roots, not with the fourth power. Okay? So let's see. 81, we could put that into 3 and 27. Split that into 3 and 9. 9 splits into 3 and 3. Remember, you are looking for groups of 4. The number of groups is indicated by the index. Okay? Sorry, that was a bad place to write that. Did not come out nice. All right? So we set that equal to. So that means we have the fourth root, and we circle up our 3s. Remember, we're looking at groups of 3, so we got 1, 2, 3, 4. There it is. Okay? And then we write 3 times 3 times 3 times 3. Okay? I'm just showing you the proofs behind this. That way we get 4 square root of 3 to the 4th. 4 cancels, and we're left with just 3 as our answer. Okay? That's it. Now, do you need to show these 2 steps in here? No. But I'm showing it to you so you can see how the proof is breaking down. Okay? Now, for more simplistic ones, you don't need to show this. But for ones where you're going to have multiple prime numbers, might not be a bad idea. Okay? So, we got 2 more left, and then I'm going to let you guys work on the examples on the other side, and then those will be, we'll go over those the next class period or in the next video. All right? So, for the fourth root of 16, again, we break it into 2 and 8. Break that into 2 and 4. Break this into 2 and 2. Again, we're looking for groups of 4, where that is the index. So that means that we're going to have 1, 2, 3, 4. There they all are. So we have the fourth root of 2 times 2 times 2 times 2, which can be simplified to the fourth root of 2 to the 4th. The 4 cancels, and we're left with 2. I should actually cancel out both 4s. That way you guys can see where that's going. Okay. And when you cancel out the index, you're canceling out the root, aka the radical, as well by default. So you're probably thinking, wait, do those numbers go to 1? No, they don't. You're canceling out the whole radical. It is the fourth root. Okay? Finally, we have 2. We have 64, so we have 2 and 32. And we're looking for sets of 3. So then we have 32. We got 2 and 16. We've got 2 and 8. Then we have 2 and 4. Then we've got 2 and 2. Okay? And it wants groups of 3. Again, the index is 3. I'm not going to write it that time. I'm just going to underline it. So we've got 1, 2, 3 here. We've got 1, 2, 3 here. Okay, that means that after all that, we're going to have the cube root of 2 times 2 times 2 times 2 times 2 times 2. Yep. However, something you should note. You can write the cube root of 2 to the 6th power. The problem is that doesn't cancel very pretty now, does it? No, it doesn't. What you can do is you can do this. You can do 3 radical 2 to the 3rd times 2 to the 3rd. And those 3's are all going to cancel and give you 4. All right. I actually kind of skipped a step there. Hold on. Should be equal to 2 times 2, which equals 4. And there you go. Okay, that completes that. Now, alternatively, I will do this again on the back side here. So 1 second, let me just show you. All right. Alternatively, if you wanted to do what was once just said, the cube root of 2 to the 6th, you can do this. That's fine. But that means you're going to have to convert it. You can't cancel. So that means you're going to have, this is the numerator, denominator. There we go. And I get 6 divided by 3 is 2 squared, which gives me 4. And there's my answer again. Okay. So if you want to go this alternate route, perfectly fine. Okay. But just keep in mind that you're still going to have to convert it. With the other method, in terms of solving, you don't have to convert anything. Things will just cancel out for your own. Okay? And that pretty much completes that.